Hi, my name is Gerard O'Reilly. I'm Associate Professor of Structural Engineering at IUSS Pavia in Italy. What we're looking at today is the Djura online platform, specifically the hazard module and the ground motion record selection tools that are available as part of that. So if I click in here, I can see a number of options that are available to me. In a previous video, we've looked already at the uniform hazard selection, where the main focus of this is trying to select ground motion records according to what the building codes require. And we saw a couple of examples from around the world about how we can do that pretty easily using the tool available there. So today we're going to focus on this one here on the right hand side called the unconditional selection, where the idea is that for a given earthquake rupture scenario, what are the intensity measures of interest we want to pick our ground motions based on. So using some ground motion models and knowing this earthquake rupture scenario, we can have an expected distribution of these intensity measures. And what we're going to try and do using this tool I'll show in just a moment is to pick ground motion models that are representative of this expected distribution. So we have ground motions that are going to be representative of the expected distribution of shaking for a given earthquake rupture scenario or scenarios in this case. So let's click here and see what we have here. So we can see on the left hand side a number of different options have appeared. So we have the GMMs, which we'll talk about just now, scenarios, advanced input, and the logic tree, for example. And over here on the right hand side, we have a couple of buttons that are going to help us along the way. And these are referring to different actions we can take as we go along. So the first thing we do is we add a intensity measure and ground motion model pair. And when we do this, we can see a little dialog box appears on the screen in front of us. And what this is asking us is basically which intensity measures are you interested in. So if we go for any of the options we have here already implemented, so for example, we have duration, filtered incremental velocity, peak ground acceleration, peak ground velocity, spectral acceleration, and also average spectral acceleration as well. So we can go for the classic example of spectral acceleration. We just input that there. And based on what we've chosen now in terms of intensity measure, it's going to ask us, okay, which ground motion models do you want to use to predict the expected distribution of the shaking? Okay, so the default value here is the Aristotle et al. 2024, but we may also want to add some other ground motion models that are available within the platform right here. Okay, so we can go and we can see which ones we are interested in. We can add the Bohr and Atkinson one, and we can also add another model from 2011, for example. Okay, so these are just some examples of what you can input here. So we're happy with that, and we can see the logic tree for this intensity measure and ground motion models is appearing and is populating on this screen below us in this little animation here. Okay, and we can see the respective weights. We can adjust these if we like. We can say something a bit more personal. We can say 0.4, 0.4, or maybe not 5, 0.4, and 0.2. Okay. And basically what we've done is we've just adjusted the weights of these different ground motion models to predict the spectral acceleration. Okay, and that's fine. But the nice thing about this tool now is that it allows us to add in different intensity measures. So we've already added in spectral acceleration, but let's say we're interested in controlling also, or at least conditioning on the expected distribution of not PGA. I was going to pick a different example of PGV, for example. Okay, so we can add this in as well, and we can pick some other suitable ground motions based on that. So we can add in, we can remove, let's say this one here, and we can just pick a single ground motion here in this case. And that's fine. And we can see that the weight is going to be 1 because we're just using one ground motion model to predict the distributions of peak ground velocity. And lastly, we can add in a different definition. So let's say we want to look at significant duration between 5 and 75% of RAS intensity. We can add this one here. And we can also see some other models as well that are available based on this IAM. So we can leave the Aristotle et al. Model from 2024 there. Or we can add, let's say just for the sake of example, we can add in another, say the Bohr and Atkinson model here as well, which will be weighted equally 0.5 and 0.5. Okay, so what you can see here is that we're not just focusing on a single intensity measure, but also on several other different kinds of intensity measures. So we're looking at the spectral acceleration, but also the peak ground velocity and the significant duration. So while this is a conditional distribution of these different IMs, it's generalized in the sense that it's not just spectral acceleration focused. Okay, so this is one of the big advantages of this tool that we've developed here and made available. Another thing that is quite nice is that if we go up here, we can click on this download button. Essentially what this does is it downloads the intensity measures and ground motion models into a JSON file. So this is essentially like a dictionary or a text file. that will just report all of the information that has been input on the screen in front of us in a handy little JSON file that we can record and document what we have input into the platform right in front of us. This is also quite handy because it allows you to see the format of the inputs in this dictionary format. And later on, we'll see how we can actually go in future cases. If we know what the format is, we can tailor this on our own local machines, do some coding, and we can upload and validate the input data directly from our machines instead of manually inserting like this every single time, okay? So we can go ahead and we can try and validate this input data, but what it's telling us here is that the scenarios are missing. And this is of course, this is the case because we've just given information about the intensity measures we're interested in and the ground motion models we want to predict them with, but we've given no information about the actual earthquake rupture, which is the next little dialogue here on the left-hand side. Now, one thing that wasn't mentioned is that depending on the intensity measures and specifically the ground motion models that were chosen on the previous step, the required input parameters for the scenarios are going to change depending on that, okay? So the first one that pops up here is the site context, because most ground motion models will require some information about the actual site. In most cases, it's the VS30 value. In this case, we can see a default value has just been inserted as a placeholder to help us along with this example as 800 meters per second. These are the parameters here. If you float over them, you can see that a little dialog pops up to give some information about what they are. But of course, for more information, you can go and look at the specific ground motion models and the associated publications with them. So we're not going to change anything here. We can just confirm and save the changes again. And what we want to do here is we want to add a scenario. So we want to add a rupture scenario. And we can see this little dialog box pops up when we click on add scenario, and this is going to have some default values again just to get us going with the example. And these are examples of a rupture scenario and some of these parameters that are required for the ground motion models that we are using, okay? So this is what I was mentioning before. If we had chosen different ground motion models, there may have been different options here. So for example, the rupture distance, the Joyner-Boer distance, or for example, this other parameter here, the perpendicular distance to the rupture. This may not have been required, for example, if we have chosen ground motion models that have fewer input parameters, okay? So depending on the amount of ground motion models you adopt and the required input parameters, this dialog box will update accordingly, okay? We're not going to change anything here. We'll just leave this all this exactly as they are. And what we're going to do here is we're going to add a second scenario. So maybe not this earthquake rupture scenario. We want to add a second earthquake rupture scenario, okay? So we'll just make a small modification here for the sake of this example. And what we're going to do is, okay, we're not entirely sure about the magnitude. We may want to include a different example. So instead of 7.5, we can include a 7.3, for example, okay? And that's something, a small modification we're going to make there. The weight is 1 and 1. This is this essentially means they're equally weighted. We could have just put 0.5, 0.5, but the program automatically accounts for this anyway. It normalizes everything to 1, so this is not an issue, okay? So these are the rupture scenarios, the site context, the intensity measures, and associated ground motion models to predict them were defined in the previous step. So we can go ahead and try and validate our input data. And we can see this works out fine. All of the input has been validated successfully. And now we can move to the next step, which is to look at the logic tree. What is the logic tree? Logic tree is essentially the map of everything we have input based on the rupture scenarios, the intensity measures, and the ground motion models, okay? So we can see the logic tree information is populated in a table here. So this is all basically a string or a dictionary of all of the information, the total weights, the ground motion models, the intensity measures, and so on and so forth. We can even search for particular things here just to verify that everything is as we expect. But probably the most interesting part of this is the diagram shown here below. And this is quite nice because essentially what it's showing us is a graphic map of the different scenarios. So for example, the rupture scenario 1, rupture scenario 2, the different intensity measures, so spectral acceleration, peak ground velocity, and the significant duration. But also if we click in here, we can see the different ground motion models we're using to predict them. For example, in the case of significant duration, we have 1. In the case of peak ground velocity, we have different 2 ground motion models here, okay? And we can expand all of these out and see these see the complete logic tree for the different scenarios, different IMs, and different ground motion models that we're using, okay? And this is a very nice way to graphically visualize the unconditional selection it is that we're doing here, okay? And the nice thing is we can download this figure, so we can save this image, Okay, we can save this to our machine and use this for presentations just to illustrate what exactly it is we're doing. And the other example, the other feature we have up here is the ability to download the logic tree information. So this is downloading the information into a JSON file format like we had before. I didn't mention this in the previous step, but we can also download these scenarios into a JSON file as well. So you can see basically the dictionary format of this input parameters we've inserted here into this user interface that can be used a bit more programmatically in the future. Okay. So this is the logic tree information, and that's all fine. We've seen, and what I mentioned about this downloading this JSON files is that in the future you can just directly upload these JSON files, and these windows will populate themselves with the input information. Okay, you can go ahead and validate this. We've already done this. We've seen the logic tree. You can go and download all of this input data, like I was mentioning. So all of these individual pages, you can just download all of that collectively. But we're happy we can just go ahead and create the target distribution. So we can go over here to the target visualization, and what we see is essentially the predicted distributions of each of the intensity measures that we are interested in. So what we're looking at here on the top left-hand side, so this first example here is the spectral acceleration. It's the natural log of it, so this is why we have the negative numbers here. So we have the predicted targets, and we'll have the individual branches of the logic tree. So we can see that the ground motion models are generally the same, and the overall target is shown here as well. So we can see the overall picture of what it is we're trying to use with the different intensity measures, in this case the spectral acceleration. Below we can see we have the combined for the different branches of the logic tree, so this is the overall target, okay, and the dispersion here on the right hand side, okay. And then the non-period dependent intensity measures like significant duration and peak ground velocity are shown over here on the right hand side. We can download all these figures, we can zoom in, we can check out particular values. You know, we can look in at particular values here. I zoomed in too far, so we can reset all of this and go back to exactly where we were. We can interact with this figure and look up specific values. We can turn off certain branches and see, just look at certain branches of the logic tree. And we can restore everything to how it was before. The other nice feature here is we can look at the actual data. So there's a lot of information plotted on this figure, but we can see that we can directly look up the data here and download this as well. And download this figure, like I mentioned before, we can save the figure and use this for our papers, presentations, or whatever. Okay. So this is the target visualization. So we're pretty happy with our target. We want to go ahead and select our ground motions. So the first thing we do before we go to select our ground motions is we want to take a quick look at the advanced input. Okay, so the default values are available here, but what we want to do is we want to just double check these and ensure that everything is how we want it to be. Okay, in the case of the input parameters, we have advanced input parameters here for the selection. We have the number of components of the ground motions. We can have a single component selection or a ground motion pair selection. So this is basically at the horizontal shaking if we want to select in just a single direction or account for both directions. We haven't implemented the vertical component just yet, but it's something we're currently working on. So it's something that will be added in the near future. So if we look at the two component selection, we can see here we have a couple of different options on the right hand side. The other menu here we can select based on the geometric mean, the row T50, the row T100. Of course, this depends on the ground motion models you're using as well. But of course, if you're doing this kind of selection, you would know about these limitations already, because some of the ground motion models are defined in terms of some component definitions and some are defined in terms of others. Okay, so this is something you would need to be aware of yourself. The number of ground motions we want to select, the default value is 4, so we can leave it at that. The significance level when we're testing the goodness of fit, we're going to leave that as 5%. And the maximum scaling factor we're going to use is 3. So we can maximum amplitude scale the ground motions up or down by a factor of 3. Okay. On the right hand side, we can see the computational settings. So we can see the number of greedy loops for the optimization. These are more parameters you can probably just leave as the default values. Don't need to change them that much. It's the random seed, the number of replications, and so on and so forth. And that's all fine. So we can save these input values. I didn't change anything, but we can just confirm it anyway. And the next option here is the intensity measures. Okay, so we selected spectral acceleration. Okay, and we can see the number of items. We can include as many as we like here. We can see all of the different ground motion intensity measures, right? And when we specified the spectral acceleration, we could see the we didn't define any information about the period. Some default values of period were selected for us, and we can see these are shown here in the complete list of intensity measures and the individual weights as well. So we can adjust these weights, and everything else will account for it accordingly. But let's say we want to add a different period. So we want to add the spectral acceleration at a period that is not listed here. For example, 1.2 seconds. So what we can do there is just import 1.2, hit enter, and we can see that it gets added to the list. The weights get adjusted, and we can get going with our selection. Okay, we can add a few more of these. These are relatively limited, just to speed up the selection. But we can add a few more periods if we want. Okay, and if we have any other kind of period dependent intensity measure, these will also pop up here, and we can adjust those accordingly. Essentially, what we're doing here, these are our filtering criteria for some of the candidate ground motions that we're going to adopt in the selection, right? So we can filter, we can say we don't want any ground motions from earthquakes that had a magnitude less than 5 or higher than 7. We can also impose some limits on the rupture distance, the number of data points, the significant duration of these, and so on and so forth. So we can have some kind of control on the kinds of ground motions we want to get out from this. So we can save these changes here, and that's fine. So we still have the same old target. We'll just redefine the target because we actually added a second, another period to that. We can go ahead and perform the record selection by clicking this button over here, and we can see that it popped up, but it's already gone again, is that the record selection was successful, and we can see that because it has popped up here on the left hand side, right? So we're going to visualize the record selection. What we see now in this case is essentially the same figures we had before. So we had the period dependent IM, which was spectral acceleration. So we can see its plot versus period, and we can see the selected records, the median of those, the percentiles, and also the target. Okay, and we can turn off some of these layers, and we can see the if we want to populate with the target and the selected median as well. So we can see that this is the overall selection is went pretty well. And of course, we can add all of these back. We can look at the tabulated data, close that, reset the figure, and we can also save this image as a image on our local machine. Probably the more interesting part of this is the figure that is just below this. So we have an option here, a drop-down menu. We can look at the different IMs we had before. So we can look at, for example, like spectral acceleration at 0.5 seconds. And essentially what we're looking at here is we're looking at the cumulative distribution function. We're looking at the overall distribution of this with respect to the target, and with respect also to the bounds we had set based on that 5% tolerance. So if we go back here, we can see the fitting at the different periods. Okay, so we can see at spectral acceleration of 1 second, the empirical distribution of the 40 ground motions we have picked versus the overall target for the specific scenarios and IMs and ground motion models we had. This is all for the spectral acceleration. So in this case, essentially what we're looking at here for spectral acceleration at 1 second is we're looking at the matching here between this distribution of these gray individual records and the distribution of the target, which is specified here. So this is like a cumulative distribution of the slice we would have at this period here, and so on and so forth for 1.2 seconds, for example, and so on and so forth. But the nice thing here is we can go ahead and we can look at the other intensity measures, the non-spectral acceleration-based intensity measures that we were interested in. So we had, for example, the peak ground velocity, and also we had the significant duration, okay? And we can see that basically what we've done is we've done ground motion selection based on several different rupture scenarios. So not just a single rupture scenario, several different IMs, which is essentially just a generalized unconditional selection with different ground motion models. So for each step, the selection of an IM, the selection of a ground motion model, and a given rupture scenario, this has been generalized so that multiple of each of these can be accounted for in this overall ground motion record selection. And we can see that the tool is relatively fast. It selected 40 ground motion records pretty quickly. The matching is very good. We can save all of this, interact with it. And also if we scroll down here, we can go and download the scaled records. Okay, click on that. It will prepare a zip file for us, scale these records, and provide them locally on our machine. And we can see this pops up and everything is prepared for us. We can scroll back up to the top. We can download the selection output. So this is, let's say, a summary. It's a JSON file of the summary of the selection. So what we're viewing here on the screen. So all of this data, not necessarily the ground motions themselves. It's more of a summary of the overall process we've just inputted here. So that's basically it. So here we've looked at a simple and fast ground motion selection based on the unconditional spectra for given IMs, selected ground motion models, and rupture scenarios. So this can be used to identify the shaking for a given rupture scenario, knowing that the distribution of IMs for ground motion and intensity measures are going to be selected and going to be represented and consistent with respect to what well-known ground motion models will be predicting for those rupture scenarios. Okay, so we've tested this. We can see it works quite well. It's quite flexible. Has a lot of features, but if you need any different features or something specific added, you can just let us know. So this video is just summarizing how to use the graphical user interface for the record selection, which is handy to visualize, but also we can see that this can be used with individual files like the JSON files. You can download and modify yourself, re-upload them. But also the nice thing about this is that this is also going to be available as an API web service. So basically you can call this from your own local machine within your own workflow. So let's say you're working within Python, you have all of these inputs locally on your machine. So the JSON files, you know which intensity measures you're looking to investigate, the ground motion models you want to use for each one of those, and the scenarios you're interested in. You can just directly call these with a single command from your Python workspace or MATLAB or things like that, without having to use the user interface. But this is a handy way to generate the initial file, let's say. So this is something that we're quite happy with. So this is just one of the ground motion record selection tools that we were offering here. So if you want to get in touch to know more about the service, visit the website, drop us an email, all of the above. And yeah, stay tuned for other videos and contact us if you need any more information.